Hello and welcome to video 7 of Functional Justin. I'm kind of excited about this one because I wasn't excited initially about doing a monad video because there's a million monad videos, tutorials. But once I started to dig into it a little bit, started to get excited about the idea of presenting monads in a different way. So what we're going to do is start with the category theory, and then we're going to present, then we're going to implement the monad using Scala. Just as the category theory describes, and I think that's an interesting way to do it. So normally when I talk about monads, I explain them in terms of monad being a useful type class. So it has a pure function, and it has a flat map function, and you can use it to take two higher kind of types, two effects. You can use it to compose them together, and if you know that, you can use monads no problem. But if you're curious, and that's why I gave this video a sort of clickbait title, it's Monads for the Genius, maybe it's not satisfying to just be told, yeah, it's just the way it is. Monads have pure and flat map. What we can actually do is figure out why monads have pure and flat map, and we can start from the beginning. So in this video, what I'm going to do is begin. We're going to be talking about monads from their origin in category theory. We're going to look at the category of Scala functions. So just normal Scala functions form a category from category theory. Then we're going to look at the category of Kleisli arrows. And Kleisli arrows, a category of Kleisli arrows is going to help us form a monad in a theoretical sense, and then we will be able to make our own monad. So we'll be able to encode what we came up with in category theory into Scala. And then finally what we'll do is flat map does not explicitly come out of the category theory, but it's a useful function nonetheless, so we can go ahead and derive flat map from the functions that we do come up with. So I've got to do a quick obligatory category theory introduction. So in category theory, if you don't know, it's a branch of mathematics that is quite high level. It's a generic way to describe a lot of mathematics. And there's some very simple concept at the beginning of it, and I don't pretend to be an expert in category theory, but I think at this point I know enough to give you the introduction and to give you enough information to derive a monad. So what is a category? It consists of some objects, and those objects must have morphisms between them. So here we have a morphism from object A to B. So if you follow that morphism, or you can just call it a transition, it takes you from one object to another. Another thing that every category has to have is an identity morphism, which is just a way to go from an object back to itself. The other thing every category must have is compositions of morphisms. So here you can see we've got a morphism F that takes you from A to B. Then we've got G, which takes you from B to C. And then if we were to compose F and G, that would take you from A to C. And the last thing you need to know is that morphisms have to be associative. So associative is something that we come across in high school algebra. What it means is, if you have some expression, say a plus b plus c, it doesn't matter if you add a to b first and then add that to c, or if you add it the other way around. So from our category here, what we can do is we can say, let's say we have a function that composes, we can compose the morphism f and g, and then we compose that with h, right? And that has to give you the same result as composing f with the composition of G and H. So that is the essence of category theory. Now what's interesting about this is that the essence of category theory is composition. And you can also say that the essence of functional programming is composition. You know, the reason behind most of what we do in functional programming is so that we can compose things from smaller parts. So there's obviously a direct link between the two things. One thing we can do is form a category of Scala types and functions, right? So there's no monad stuff here, no Kleisli stuff. This is just three normal Scala functions. So if we make a category that consists of Scala types and functions, if you remember on my category diagram, we had the objects A, B, and C. They would be Scala types, so integer, Boolean, and string. And then we've got these functions that map between those types. So we've made these functions, and then we can compose them. So Scala has a function compose that lets you take two functions and compose them together. So this is just a way of expressing, let's say we had f and g, we wanted to compose them. We could call f first, and then we can call g on the result. So compose will actually take two function objects like we've got here, compose them together, and then we can call them. So to be a category, we need to follow the laws of being a category. I mentioned that we have to have an identity morphism. Not only do we have to have one, it has to behave itself according to these rules. So composing a function, which is the identity, with any other morphism must be the same as just calling that morphism. So if you look at the code here, we have a function f. If we compose that with the identity, that has to be the same as just calling f. So that's kind of the idea of an identity. The next thing we've got is composition has to be associative. So we talked about it being associative. What that means in this case is, let me just move me. What that means in this case is that composing h has to be, composing h with the composition of f has to be the same as composing h with the composition of g and f. So these two concepts of identity and composition, they're going to be very important when it comes to deriving what a monad does. So the category of normal Scala functions is just of interest, but where it becomes much more interesting is we make a category that consists of Scala types and Kleisli arrows. So what is a Kleisli arrow? Well, a function just has the type A to B, right? So it maps type A to type B. So a Kleisli arrow just maps an A to an f of B, where f is some functor, right? So we've already talked about functors and mapping things, and we've seen that this kind of function signature shows up a lot, where we start with a pure value and then we end up with some kind of effect. So Kleisli is really just that function, and you might recognize that as being the input to a flat map. So if you have some effect, you apply a function that has the signature to it, it gives you the ability to sequence those two effects together. So that's kind of what we're trying to get to. So what we're going to do is imagine a category that consists of two things. Instead of normal functions, we have Kleisli arrows, and instead of the identity function, we're going to have a function that has the signature a to f of a. Now, if you've seen the monad type class, you'll know that that's the same signature as pure, right? So we're going to call it unit, but essentially we're going to have two functions, unit and compose, which have direct analogs to what we were looking at with the Scala function category. All right, that's enough of me, and now we'll go to the code. So what we're going to do is make a type class that is a monad, but it's going to be a bit different to the monad we've seen in the earlier episode. It's going to be a monad that maps more directly to the category, so more specifically the category of Kleisli arrows. So what we want to do is we're going to make a monad, and we'll just call it monad 1 to differentiate it between the monad we're used to. And what we're going to do is add a couple of functions that we can then use to represent the identity morphism and the Kleisli arrow composition. And between those two things, we can make a monad. So first of all, we'll call the pure function, we'll call it unit, because that's typically what it's called in the mathematics. So unit in mathematics just means some kind of identity. So for example, you multiply numbers by 1, you get the same number back. So that's why we're going to call it unit. It takes a value of type A, and then it returns a embellished value or effect value of fa. So for any effect that we implement, and by effect we mean things like options and lists and futures, and we're going to see more things like zeros and Monads tasks. These are all effects that we can use to do interesting things, and they can all be used with monads. Okay, so we've got the identity function unit, and now we're going to have a function called compose, which allows us to take two Kleisli arrows and compose them together. So if you remember from the diagram, we had 3 different types involved, because we're going to map from an A to a B to a C. So we're going to need 3 types for those. We're going to need 2 Kleisli arrows. So let's call one LF, and this will map A's to to FB's. And then we're going to have a second one, we'll call that the RF, and that's going to map B's to FC's. And then that's going to return an FC. Alright, so between those 2 functions, we can model the category theory category of Kleisli arrows. So to make this real, well, first of all, let's just make a companion class. And what we need in the companion class is to make an apply function. This is just a practical thing so that we can always easily summon a monad of this type if we need one. And all that does is it takes an implicit argument of the type monad f, and then we can just return the m. Oh yeah, and I've got to use my superhero name for monad1, and like that. Alright, so now we can summon the monad into existence as long as we have some kind of instance for it. Now I guess the next thing we need is some instance of the monad. In this video we're going to be using option as our effect. So remember that option is an embellishment on a pure value, which allows us to treat that pure value as maybe it's there, maybe it isn't, right? So it represents the effect of a missing value and lets us write pure programs, referentially transparent programs that can work with potentially missing things. So we're working in Scala 3, remember, so we're going to use the given keyword to create an instance for the monad. So we're going to give it the name option monad1, and then this will implement monad1 for the type option. And what we need to do is implement both unit and compose. The implementation of the unit function is quite straightforward. It takes a pure value of type A, and then all we need to do is wrap it using the effect constructor. So in the case of option, we just use the option constructor, and that's all we need to do. The compose function, what this needs to do is compose 2 Kleisli arrows, right? So we've got the left function and the right function. So we can copy the signature from up here and use exactly the same thing. And then we have to replace these parameterized types f with the actual effect type we're dealing with. So that's option in these cases. So what do we need to do to implement compose? You can see from the type signature, oh, I do apologize, the type signature is wrong. So the way that compose works is it takes 2 Kleisli arrows, but it actually returns a Kleisli arrow. So the input to this one is going to be the type A. So from the diagram, if you remember, we give it an A, and then it's going to go through the chain of the 2 Kleisli arrows, and then at the end we'll get the type C. So apologies for that, and let's just update this one too. Okay, so because we want to return a function, obviously the first thing we need is a parameter. So we're going to make a function. What we're going to return is a function that returns takes a parameter. The next thing we want to do is call one of these functions on our parameter. So if we call LF on A, then what that returns is going to be an option B, right? So what we're doing is we're calling this function, and we're going to take the A and materialize an option B. And then we can do just a simple match on that because we're just dealing with options. So what we want to do is, in case there's a value in it, we know that it's going to be a value of type B, so we'll call it B, and then we can call the write function on that. Remember that the write function takes a B and returns an option C, so we can match on that, and we can say for some C, what do we return in this case? So we can just return option C, and if that option was empty, we can just return none. And this case here, case none, also return none. This should be more like this. Okay, so what we've implemented there is a way to compose two Kleisli arrows, and that's essentially all we need to use two options together with Kleisli arrows. Okay, so that's everything we need to do to implement the instance of monad 1 for option. So now let's look how we use it in real life. So we'll make some contrived functions that meet the type signature or the shape of Kleisli arrows. So remember, a Kleisli arrow is just a pure value, a function that takes a pure value and maps it to an effect, and our effect is going to be option. So we can make some functions that do things with pure values to options. So for example, this function is just going to return an integer unless it's 4. So if the number is 4, we'll return none, otherwise we'll return a option of the number. So that's our f. We'll make a function g, which takes an integer as well, and returns an option boolean. Now remember, when we're composing Kleisli together, the type inside the effect, so int and boolean in this case, can change between the 3 steps, but the actual effect type can't. So everything's going to be an option, but what's in the option can change across each function boundary. So this one we're just going to say if the number is an odd number, then we'll return true. Otherwise we'll return an option false. And then we need 3 functions for what we're going to do next, so let's make another one. So this one will take a boolean, and return an option string. So what we'll do is we'll just say if B, if it's true, then we'll return some string. Otherwise we'll just return none. Now if we had our monad that we already implemented, we could use Flatmap to sequence these things together. So remember that the purpose of monads is essentially to take these kind of functions and apply them to effects. So we can map an FA to an FB using Flatmap. We do have a monad, but we don't have Flatmap. So let's see how we can compose them together. So remember that the compose function returns a function. So we'll capture that. We'll say fcomposed is going to be equal to monad1. So we're going to summon it into existence using our apply function that we made. Then we can call the compose function on it. And then what we're going to do is compose 2 of our functions f and g. So the type of this will be something that takes an integer and 2 Kleisli arrows, and it will dump us out an effect of type boolean, an effect of type string at the end. So fcomposed is a function. So now what we can do is we'll call that a few times with some values. So it's going to be fcomposed. Let's say we'll call it with the numbers 1 to 4 so that we can see that it's working correctly. Don't need that one. Okay, so let's run that and we should see the output below. And there you go. So the first one is true. Essentially what we're going to see is an early exit if the first one is 4, right? So you can see that in the last output, which is none. Whenever we get an odd number, we're going to get true, and whenever we get a even number, we're going to get false. So that composes F and G. What we might want to do is also compose H. So we can call this the composition of F, G, and H. And this is also going to give us a function. And what we can do is compose F composed with H, and that gives us the whole all three functions composed together. So when we run that, we'll see that the output will reflect the winner string. But first I have to actually call the new function. There we go. So now when we run it, we can see that it's going to have the correct output. And we have 2 winning cases. Alright, so we have a real monad now. We can use it to compose effects. So the next thing I want to look at is the monad laws. So the whole point of making monad like this was because we wanted to reflect the monad from category theory more closely. So let's see if we can actually map the monad laws to using our new monad. So the first law is the identity law. So what that says is that if we let me just bring a monad into existence. We'll call it M1. I'm going to call it monad 1 for option. So the identity law states that if we compose a function, so we can say f with unit, and then we'll pass in some input value, that should be equals to just running the function itself. So that's called the left identity, and I'm just going to print that so we can see whether it's true or false. And the right identity is the same thing, but the other way around. So we can say f1 is equal to composing f and unit like that. So this is the left and right identity. We're going to run that, and you should see at the bottom that these are both true. The other thing we want is remember that composing the Kleisli arrows together should be associative. So that means that if we have the 3 functions f, g, and h, we can compose f and g together and then compose that with h, or we compose f with the composition of g and h. And so if we can do that, then the associativity morphism is good. So we can call that the associative law. And I'm going to spell associative correctly. And so what that looks like is we're going to print it. Associativity is going to compose M1 composed with f and g. If we compose that with h, that should be equal to composing f with the composition of g and h. Now if I was to compare those, that would be true too, but that's not quite correct yet, because what we're doing there is we're comparing 2 functions, and sorry, that's false. So the 2 functions are not the same, but what we should be comparing is the result of calling these functions. So let's pass in the parameter 1 again, and then when we run this, we should see that the associative law holds. And there we go. So to this point, we understand why monad consists of these two functions, and how to implement it, how to make an instance of it for option, how to use it, how to compose multiple effects together. The last thing I want to talk about is Flatmap. So when you look at the implementation of Monad, we pretty much always see the identity function, which is called return or unit or pure. Then we see Flatmap. So the reason is that Flatmap is more useful. We can compose things together, and you can see that it's if you're familiar with using Flatmap, which I'm sure most Scala programmers have used Flatmap a lot, you can see that it's a lot clearer than composing Kleisleys together. So the question is, can we implement Flatmap with these two primitives? And if we can, then we know that we can implement Monad with unit and compose, and we can still use the Flatmap that we know and love. Well, we'll just implement it as a function, but we could also implement it as a derived extension method in here, so that we can then just use it like any other monad. But I'll implement it here just as a function so that we can see what it looks like. Now the implementation is a little bit tricky, but it's interesting, and it's nice to see that it's possible because it has some interesting properties. So we've got a flat map. We need a monad of type F, and we need the types A and B. And remember, the input to flat map is a type FA, and the output is going to be an FB. And as well as that, we need a function, and the function is going to be an A to an FB. And the last thing we need is a monad in scope. So let's say we're using a monad, we're going to call it M. It's going to be a type monad 1, and it's going to be of type F, specialized for F. And the return type is FB, and there we go. Alright, so what we want to do is implement Flatmap using compose. Alright, so let's begin with just composing. Essentially what we want to do is pass FA into the left side of the composition. So what we do here is a little bit tricky to understand maybe. We need a type FA. I'm just going to put the actual type in to help the compiler here, because otherwise it won't work. So what we're going to do is we're going to take a type FA. We're going to pass in FA. So that might be confusing, but it will probably make sense in a moment. And then on the left side, we're going to have a function that takes a parameter A, and then it applies the function FA. And then at the end, we're going to call all of this thing on FA. So that's what Flatmap looks like. I'll come back to just talk about that implementation in a moment. But let's just use it so that we know that it works. Okay, so let's just call Flatmap on F1 on our F function. So we can call F. We can call Flatmap, and we can pass in F1, which is a Kleisleys arrow. So remember, the first parameter to Flatmap is the FA. So we can get that by calling F on 1. And then the next one is another Kleisleys, so we can pass G for that. So what we're doing is we're composing F and G. So it should look like that. So if we run it, it should be the same as composing F and G from above. And you can see we got true. Okay, so the upshot is that Flatmap can be implemented with compose. So what that means is that Flatmap and unit and compose is essentially the same as unit and Flatmap. I'm not going to do it in this video because I don't have time. You can also implement compose using Flatmap. So how does this Flatmap work? Well, remember that Flatmap has two Kleisli arrows that it's composing. So the first Kleisli arrow looks like this. It takes an FA and it returns an FA. So remember that when we pass this function in to the compose function, it's going to look inside the effect, right? So we passed in the FA, and what it will get is the A, which it needed. And then it's going to pass that A to the next function, which is a B to an FC. So what that will do is take that parameter and pass it into the next thing. So the second Kleisli is going to take a and return an FB. So what's kind of interesting about this is sort of a functor, because remember a functor takes an FA and returns an FB. So what this Kleisli is sort of like a functor with the identity function. And that's what we're using to make compose work. So anyway, the compose as a whole, so this big chunk, what it returns is a function that takes an FA and returns a FB. So then to get the final FB, we actually pass in the FA that comes from the argument here. Now this is probably an easier to understand implementation. We can just call this identity. And it doesn't work because we need to help the compiler a bit. Now if I was to just change this from A to FA, then it works. So there we go, just a quick recap again. What we did in this episode was looked at monads from category theory and pulled them into the Scala code, implemented the monad type class with two operations so that we could represent identity morphisms and composition of Kleisli arrows that composed. So those two things together give us what we know as the monad, and then we saw how we can use that. We can use it in practical code to do stuff, and then we looked at how to prove the monad laws. Well, not prove the monad laws because we didn't put all of the possible values in, but we can certainly see that the monad laws hold for these basic examples, and you can see the monad law, it's sort of expressed in the code. And then we implemented Flatmap using compose just to make it clear what was going on. In terms of monads consist of pure Flatmap. So hope you enjoyed this episode. So the next episode I'm looking forward to myself. It's going to be about monad transformers. So we're going to look at the writer monad, how to implement monad transformers using Scala 3's new syntax, and should be pretty cool. If you haven't seen the earlier videos, then I would suggest backtracking, take a look while you wait for the next video. If you liked the video, please hit the like button, subscribe, tell your friends and work colleagues, and thanks very much.